ISS height above the Earth. Did Dr. Zack school Red's rhetoric? So, Dr. Zack, I see you've made this video. Again, it was 3 weeks ago. Sorry, I'm late to the party. But I know that there's been a lot of back and forth, especially with Antonio and Red making different videos dealing with different things, especially triangles, isosceles versus scalene. But you know what? All real-world triangles are scalene. But we're not going to talk about that. So about your video, I did try to make a comment, but it turns out I was blocked. So I switched over to my other account, my math tutorial account. I've got 1,500 subscribers. The account's about 7 years old, so it's not a sock account. Plus, I signed my name, but when I made the comment, that account was quickly blocked as well. So. So you and I have an interesting relationship, Dr. Zack. I send you heartfelt messages, and you respond with heartfelt messages. So this is my attempt to have a sort of a dialogue, because you're not blocked on my channel. So hopefully you will leave a comment on this video. And this was a labor of love. This Apple Keynote slideshow is actually 286 slides long. So anyway, hopefully you'll enjoy it, Dr. Zack. Let's start at the beginning. For those people in the audience who don't know, Red's rhetoric proposed using parallax. Like closing one eye, close the other eye, so you see something shift against a background, to observe the ISS transiting the moon, using a website called transitfinder.com. It'll give you data on when the moon or when the ISS is transiting the moon or the sun, and stick it on a map. So Red used this information when he did a paired sighting with Astronomy Live, and he made a video about it. So here was his baseline, and again they were looking at the ISS. So this produced parallax against the distant moon. All right, so let's take a look at that triangle. Again, I know there's a lot of argument over whether that's actually an isosceles triangle or whether it's isosceles enough. But the bottom line is, if you know that angle, that parallax angle, and the baseline distance, you can actually compute the distance to the ISS. So then taking that distance and then the angle of elevation, they can actually figure out the altitude of the ISS. So that's the basics of it. So here's the still from Red's video showing the two passes of the ISS past the moon. And then Dr. Zack, here's your still from your debunking 1 month later. So it looks like you made about 6 claims. One is that Red had picked the wrong ISS path across the moon. He was 100 kilometers off. He may have made up the pixel ratio. Calculations really should involve the distance to the moon. The size and distance to the moon are actually required to find its angular size. And then a big claim of yours was that picking any arbitrary numbers will work with the same calculations. So before we begin, I just want to cover this quote from Winston Churchill. "The truth is incontrovertible. Malice may attack it, ignorance may deride it, but in the end, there it is." So people seem to really like your video, Dr. Zack. Here's some comments from your channel. "Red's just got demolished. The solid Red's flat smacking was given. Amazing work. Dr. Zack is back." And then lastly, "Red just suffered one big flat smackdown." Well, you sure told him, Dr. Zack. It's the motherfucking Eagle Double G. Snoop Dogg. So before we get started, let's bake some cookies. Do you prefer making cookies from the store-bought dough, or would you rather make them from the raw ingredients? What do they call it? Baking them from
scratch.
Baking them from scratch. Yeah, that's the way I prefer them. So, thanks. Those were delicious. All right. Number 1, you claimed that Red picked the wrong ISS path. Let's examine this claim.
Now, just to make him a little bit angry, let's skip to 44 seconds and pause. Now memorize the track.
Okay, so I did just that. I went to 44 seconds, and then I captured a couple sightings, frame by frame, putting the ISS on the moon. I was very carefully looking at those craters and stuff. So that's the first pass.
Now skip to 6:20 and pause and memorize your track again.
All right, that's what I did. I again went frame by frame and I put the ISS, based on where those craters were exactly. And those are the tracks that I got. And here's what you showed. All right.
Now at least get your tracks right, Mr. Reds. Stop fooling people who think you are good at math. You are not.
Wow. Again, you sure showed him. But I think we may be premature because if we actually watch Red's video, he clearly identifies that first track as being from Bowling Green, Florida. So that track is from Bowling Green on November 4th. Bowling Green isn't anywhere near Venice, right? The paired observation was in Venice. It's over 50 miles away. So this path was from March 3rd in Venice. Why don't we keep watching, see what we see? And it turns out that there's another track, a third track. And what does this track represent? And it's clearly identified in Red's video as being Astronomy Live's footage, also from Venice on the same moment, same day. All right, so it looks like Reds did not pick the wrong ISS path. So this whole wrong track thing, does it remind you of something? Because it reminds me a whole lot of Soundly's video, Curved Water Found. And then you made a debunk video, Curved Water Found Debunked. Now here's from 1 minute 15 seconds in Soundly's video, clearly identifying the location of these power lines. Now here's your video.
But are they really on a straight line? Let's find out. This one is easy. All we gotta do is go to Google Earth and find the power line in Lake Pontchartrain and see for ourselves if they are really on a straight line.
Yeah, it's kind of painful, Dr. Zack. Yeah, those power lines you picked are not on a straight line. So what do you think of your Lake Pontchartrain debacle? Yeah, exactly. All right, next claim. Red was 100 kilometers off when he calculated the height of the ISS. So you did a nice job at animating Red's calculations. So he found the distance to the ISS was 524 or 525 kilometers. And the actual height of the ISS is 408. So it looks like you're correct. He was 100 kilometers off. And you kind of made this little snarky remark how impressive his calculation was. Well, let's go to Red's video. What did he show? Well, if you take a look, he says, during our observation, we were seeing the ISS from 326 miles away. If you do the conversion, that works out to be about 525 kilometers. So, Dr. Zack, it looks like you got this one as well. But, again, why don't we actually do a crazy thing, and that's continue watching Red's video. So that was at 11 minutes 34 seconds. If you go 2 seconds later at 11 minutes 36 seconds, Red says, but we're not done here, because now we can find the altitude of the ISS. And he does just that. Using a little bit of trig, he's able to find the altitude of 419 kilometers, which is only 11 kilometers off. That's less than 3% error. And I would call that impressive. So, looks like you lost the point there, Dr. Zack. So that's 2 times in a row where if you had simply watched Red's video, just simply watched it, you would have not made these mistakes. So just tell us, how much of Red's video did you actually watch? Just a little bit. Okay, that's what I thought. All right, point number 3. Red may have made up the pixel ratio. All right, so what is this pixel ratio we're talking about? It's the moon's diameter divided by the ISS parallax. And that Red calculated to be 4.29. We'll call that the pixel ratio.
I looked up the pixels in his links, but I found no description of how he got the pixels of the moon, so I can't judge that. But I wonder if he just made it up to make his math look like that. Kind of accurate. The most important number of everything he has done looks made up, and it has to be made up.
All right, let's take some quotes. I found no description for how he got the pixels of the moon. but I wonder if he just made it up to make his math look like that. The most important number of everything he's done looks made up, and it has to be made up. Wow, you sure told him. But let's actually analyze. Let's analyze this sequence of statements. In other words, let's kind of go inside the mind of Dr. Zack, right? Let's go inside your mind. So, first statement, I found no description. Well, that's a statement of ignorance. And I'm not trying to insult you. Everyone's ignorant of something. For example, I don't know how sunscreen works. So there's nothing wrong with being ignorant. But then you take it to the next level. You turn that ignorance into speculation. You wonder if you made it up. And again, anybody can wonder about something. There's something wrong with that. But now you actually say that it looks made up. So you're making a quote-unquote observation. And then finally you say it has to be made up. Like you actually are stating this as if it's a fact, that this pixel ratio had to be made up. And I'm not amused either. So again, why don't we actually watch Red's video? Let's get a clue by watching Red's video. And at 9 minutes, 43 seconds, he says, in counting the pixels from Astronomy Live's footage, oh my goodness, if we actually count the pixels, maybe we can get something. So did you have trouble, Dr. Zack, counting the pixels? Here's a still frame from Red's YouTube channel, and here's a still from yours. Again, here's a still from Red's YouTube channel, and here's one from yours. I think you would have trouble counting the pixels. I'm not sure what happened to your video, but that aspect ratio is pretty whacked out. And I saw this funny thing on the side. It looks like you've got a fan club, Dr. Zack. So let's take a screenshot from Red's video, and let's say that we're not going to trust his numbers at all. So we're just going to throw his numbers out the window. What we're going to do is we're going to actually measure this ourselves. So what I'm using is Apple Keynote, and so I measured the pixels to be 670 pixels tall, and then this is 156 pixels wide. This is literally off my screen in Apple Keynote. And so I made my own pixel ratio, and I found that to be 4.29. Where have we seen 4.29? Oh, that's right. It's the pixel ratio that Red's Rhetoric claimed it to be. So again, there's danger in assuming things, okay? Let's just ask somebody. So, doesn't look like he made up that pixel ratio. Looks like he measured it, all right? Now I feel kind of bad that you've lost 3 points in a row, so maybe you can help me out a little bit here. I was doing this flat earth crossword puzzle, and I just don't think like a flat earther, so I don't really have the mindset. So this one clue has really got me stumped. 9 across. All right, so it's an 11-letter word for panacea. I don't even know what that means. Could you help me out?
And the flat earther will answer perspective.
Ah, perspective. Look, it fits. Dr. Zack, you're a genius. So, looks like you got on the board. You finally got a point, Dr. Zack. How does that make you feel?
Oh my God, it's full on. Double rainbow all the way across the sky.
All right, settle down. Settle down, Dr. Zack. Okay, we're on to number 4. Calculations involve the distance to the moon. So let's go through Red's procedures. So we have 2 observers, about a kilometer apart. They make their observations, stack the images, we calculate the pixel ratio, and then using the angular size of the moon and the pixel ratio to find the angular width of the parallax. A little bit of trig gives us the distance, a little bit more trig gives us the altitude of the ISS. But Dr. Zack's procedures are a little bit different. First off, we're starting with the same observations, but instead of measuring the pixel ratio, we're just going to assume that Red's pixel ratio is correct, and then rely on Google for the size and distance of the moon, compute the angular size of the moon in radians, and then convert to degrees using Google, and then just assume that pixel ratio is probably a fake pixel ratio anyway. But step 4 is the same, using a little bit of trig and the baseline distance to find the distance to the ISS, but you skipped step 5, Dr. Zack. You're pretending that distance is the same as altitude. So that's a little problematic. But we're not going to focus in on that last part. We're going to focus in on the part where we're actually finding using the angular size of the moon. So your accusation is that, I don't know, that the Red's just like using Google as opposed to measuring it. All right, so let's go to Red's video, and it looks like he is using Google.
You can do a simple Google search to get the angle of the moon. Smiley face. What an idiot this guy is. He puts his whole trust in the hands of Google Info. Proudful. Smiley face. Dr. Hack, brilliant work.
Yeah, looks like you got him there, because you can just make up numbers, right? You're just using Google numbers, you just make them up, and wouldn't that give you the answer? But not so fast. Not so fast, Dr. Zack, because we can actually see the moon. The moon is observable from viewers standing on Earth, which means the angular size of the moon is observable from viewers on Earth, which means the angular size is measurable. All right, and we're going to cover this in part 5. So it looks like that we really don't need the distance to the moon, after all. But going back to these comments, now these comments are under your video, Dr. Zack, and here's a comment right after that last one. People like Red are worried that there is a growing movement that thinks it's cool to be stupid and ignore facts. And what's funny is you hearted this, Dr. Zack. I'm not quite sure if you understood what that comment meant. But anyway, so speaking of hearts, one of my favorite video games is Super Mario. It's actually Super Mario Galaxy. It's me, Mario. So what's your favorite video game sound? Outstanding, Pac-Man. Anyway, let's go on to number 5. The size and the distance of the moon, distance to the moon, are required to find its angular size. So this was a claim that you didn't make explicitly in your video, but you did make it in comments. And here's a comment that you wrote to me.
¿Sabes incluso cómo obtienes el radio angular? Es el radio del objeto dividido por la distancia.
So basically you find the angular radius by taking the radius of the object and dividing it by the distance. So you're making a big point that you need the distance. So sorry to say this, Dr. Zack, but I'm going to have to school you on this point. So how do you find the angular size? I'm sure you would love to know. Well, one way is to calculate it using the size and the distance. Hey, wait a minute, isn't that what you said? But there's a couple provisos. Yes, you can calculate the angular size using size and distance, but only if you can't see it, right? Only if you can't see it, or maybe you can see it, but it's a non-calibrated observation, like, taking a selfie in front of the Eiffel Tower, right? So then you calculate it using size and distance. Oh, by the way, here's a side note. My favorite, absolute favorite angular size calculator is at 1728.org. And you don't need to start with the size and the distance. You can actually start with any 2 of the 3 items. Any 2 of the 3 items, and it will solve for the third. It's a really, really handy calculator and quite robust. So is there another method? Dr. Zack, is there another method to finding angular size? And the answer is yes. When can you use this method? Well, you can use it when you can make a calibrated observation. And if you can make a calibrated observation, you can actually measure the angular size visually. So what does this calibrated observation mean? So there's 3 different ways of making a calibrated observation. One is a naked eye observation, but with a reference object. Another one is calibrating a camera with a reference object, and the other one is photogrammetry. So these are sort of in order of precision. Let's start with a naked eye observation. So artists have known for years that you can take a pencil and you kind of, cinch your thumb up on the pencil and kind of get an angle. And so that angle, the angle of the cone and the angle of the pencil, that's going to be the same angle. And then you look down at your paper and you can make it the same angle as well. So that's a naked eye with a reference object. Now, in the case of the moon, what if you were to take a small pea and kind of hold it up until it matches the size of the moon in the sky? And then you measure the distance from the pea to your eye. Measure that distance. And then, that'll give you kind of a ballpark estimate for the angular size of the moon. So number 2 is calibrating your camera. And now this is a really, really good method. The reason why I say it's a good method is because I created it. Oh, I didn't create it. I have this in this video, Flat Earth Experiments, Size of the Moon. And so what I propose is that you take your camera and you stick it on the 50-yard line, and then you take a sheet of office paper and you put it exactly 50 yards away. Then if you just do the math, then you actually will get like a very precise angle. But not only that, if you take a photo with the same zoom settings. Now this is really important, like say for the P900, maybe full zoom on the P900 or something, and then full zoom, you know, you shoot the moon and then you shoot this office paper, you'll be able to compare apples to apples, right? You'll be able to compare apples to apples, and you can actually do some calculations because you have calibrated your camera. So the third method is an astrophotogrammetry. Because the stars are in very, very precise positions. The stars have been studied for centuries, and they know the positions of these things extremely precisely. So here's the constellation Orion. Let's focus in on the 3 stars of the belt. The 3 stars of the belt. So here it's Alnitak and Mintaka are the left and the right hip. And we know the right ascension and declination. That's kind of like latitude and longitude, but with great precision in the sky. So if you take the right ascension and declination, plug them into a calculator, you can actually get the angular distance between those 2 stars. It's about 2.2 degrees. So again, let's say you take your camera and it's with a very specific zoom setting. So, you know, the same zoom setting. You take a picture of the 3 stars in Orion's belt, and then you take a photo of the moon without changing the zoom. And if you measure the pixels, you can make a comparison, and you can find the moon's angular diameter in that photo to be 0.54 degrees. Right? So do you understand, Dr. Zack, that you can actually measure the angular size of something without knowing its distance? Right? Now, here's a little bit of a blind spot, Dr. Zack. Everywhere that you mentioned Red's partner, you show him as troll friend. Well, he's not a troll friend. He's Astronomy Live. Okay, he's a YouTuber. He's got a great channel. He's got almost 13,000 subscribers. And he made a video called Sizing Up the International Space Station, talking about his side of the exploration he did with Red's Rhetoric. And so he uses a website called astrometry.net. And using the observation that he had that evening from Venice, Florida, he was able to very carefully measure the angular separation of the parallax of the 2 ISS tracks. So again, the bottom line, Dr. Zack, is that angular sizes can be measured. Well, not only can be, but they actually are measured from the ground. Okay? So it looks like I'm going to have to give the point to Astronomy Live. I think it's crazy that you didn't know that you could measure angles from the ground. So show us your crazy eyes, Dr. Zack. Oh, that's classic. All right, thank you. So number 6, picking any arbitrary numbers will work with Red's calculations. Again, this was a central theme of your video because it just made it seem like it was just a bunch of math and magic.
So I will give you the distance to the moon and the distance to the ISS. I will just make up a number, of course. I actually can choose any distance to the moon, and your beautiful math will match my math.
All right, that's quite a claim. Your beautiful math will match my math. You pick any distance to the moon. So let's figure out what's going on here. So picking any arbitrary numbers will work with Red's calculations. Let's unpack that really big value you wrote. Let's see if your math procedure works with your made-up numbers, and then does it work for any numbers? So first we'll unpack that big value. So I know you were kidding. You know, you were kidding when you wrote that big, huge number. But let's actually play with this. Let's see what this number really means. So we've got thousands, we've got millions, billions, trillions, quadrillions, 465 quadrillion kilometers. So just for reference, a light year is about 9.5 trillion kilometers. That means the distance to the moon is about 49,000 light years for your example, right? So could the ISS actually transit the moon if it were 49,000 light years away? So for reference, the moon would appear to be 30 nanometers at the distance of the ISS, and the Ebola virus is about 50 nanometers. So imagine an astronaut taking a petri dish with a single Ebola virus on it and holding it up to a window, say on the cupola of the ISS, and then having you photograph it from the ground. That's how big the moon would appear. Actually smaller than that at 49,000 light years. So again, that's a silly number, but your point was that it should work with any numbers. No, it does not work with any numbers, and it clearly doesn't. Now let's go through your procedure using your made-up numbers. So one thing that you do is you arbitrarily change the distance to the moon while keeping the moon the same size, the same diameter. And this dramatically changes the moon's angular size in our sky. Now this doesn't make any sense. 1.32 degrees, that's almost 3 times as big as the moon appears in our sky. I think somebody would notice. So you can't just arbitrarily change the distance to the moon, right? Furthermore, you're using Red's pixel ratio. Now that 4.29 was based on a measurement, what's based on an actual photograph. We're counting pixels from a photograph. We actually did that in this video. And you can't just take some random size of the moon and divide it by Red's pixel ratio. That simply doesn't make any sense. So let's visualize this. So what you'd expect if you have this parallax track of this ISS, and then let's say you arbitrarily change the distance to the moon, well, this is what would happen. The parallax track would not change. The angular size of the moon would change, but the parallax track wouldn't change because the ISS isn't changing its orbit. You'd still have parallax, but by the same degree, right? So what you're saying, what you're suggesting, Dr. Zack, is that the parallax track of the ISS in Earth's orbit would change if you changed the size of the moon. And that simply doesn't make any sense, right? But for purposes of our analysis, we're going to say, Dr. Zack, let's say you're right. Let's say you're right, and let's just run the numbers using your method, okay? So does this in fact work for any numbers? So the first thing we want to do is we want to come up with a big formula, right? We're going to start with the angular size of the moon in radians, and this is, it's called the small angle rule. When you have a really, really tiny angle, you could just divide the diameter to the distance to get the size in radians. And then we divide that by the pixel ratio, and again, this doesn't make sense, but we'll do it anyway, Dr. Zack. Divide by 2 to get a half angle, take the tangent of that, and then divide that into the half of the baseline. Now this gives you a number of complex fractions, so we're going to just simplify these fractions. And this will give us the computed distance to the ISS. All right. So I'm just going to give you a side note on percent change. A lot of people don't know how to compute percent change, and it really is very simple. It's the difference divided by the original. Now, how do you find the difference? Well, that's the new minus the original over the original, right? So in terms of the ISS, that'll be the computed value versus the official value, all divided by the official value. All right, so how do we find the percent error of our computed ISS height? That's how we're going to do it. And I'm only interested in positive percent change. So we're going to take the absolute value. So any negative numbers, the negatives are going to get stripped out. Okay, so this looks like a really complicated formula. So why are we making it one calculation? Well, I'm going to answer in a couple slides. So again, the claim is that any values of the moon distance and the ISS height will work. So to test this, we're going to pick a range of moon distances and then a range of official ISS heights for comparison. Then we're going to use the moon distance to perform the Dr. Zack calculation, and then we'll find the percent error when comparing it to the quote-unquote official ISS height. And so, for example, if we have a range of 20 moon distances and 20 ISS heights, that's 400 calculations. Now that will be very tedious, so we're going to use a spreadsheet. Now here's the thing about a spreadsheet. Each cell can have only one calculation in it. So that's why we made it one calculation, because each of those calculations will fit in one spreadsheet cell. So let's take a look at what the spreadsheet might look like. So, and again, these are Dr. Zack's, these are your chosen values obviously not from real life. So you picked a moon distance of 150,000 kilometers, and then you randomly picked an official ISS height of 211 kilometers. Well, that's about a 3% error if you run the numbers. So let's actually do this for a whole spreadsheet. And so to make it easier on the eyes, I color-coded the whole thing based on the percent error. So we've got this handy-dandy do-it-yourself Dr. Zack moon distance spreadsheet. So these are the column headers. And then do-it-yourself ISS distance. I'm calling it the dist height because it's not the actual height. And again, starting value and an interval. So we're like counting by tens here. And this gives us our spreadsheet. So let's have the spreadsheet crunch the numbers. And there we go. So we see very clearly that any old numbers does not work. Some of the numbers work, right? Some numbers, some pairs of numbers work, but every number does not work. But specifically, Dr. Zack, if you had picked 160,000 kilometers for the distance to the moon, and then 220 kilometers for the height of the ISS, then your calculations would have been pretty good, right? But basically, they don't work for everything. So here's what the spreadsheet looks like, and you guys are welcome to try it out if you have a Google account. So over on the left-hand side is sort of the controls for the spreadsheet. So let's take a look at these controls. And again, you guys can play with the spreadsheet yourself. All you need is a Google account. So you could plug in all the values that you want. And let's just take a quick look at this bottom value, because what I decided to do is allow people to put in another number for an angle of elevation. So Dr. Zack, you skipped this calculation as well. It's almost like you were treating the ISS as traveling directly 90 degrees overhead. So in the actual observation that Red made, it was 53 degrees angle of elevation, not 90. So again, you can change that if you'd like. So here, let's just have some fun with the spreadsheet. So using the official published numbers, and again, maybe you can call this from NASA, but the published numbers, the actual distance of the moon to Venice, Florida, at the moment of Red's Rhetoric's observations was 367,826 kilometers. All right, and our interval, we're going to use 0. We don't want to count by tens or count by hundreds. We just want that value for the whole spreadsheet. Now, how about the actual elevation? So according to my research, it was on that date, it was 404.5 kilometers in elevation. And again, we're not using any interval. We just want the 404.5, and we're going to stick with it. Now we know from the actual measurement on the ground by Red and his friend, Astronomy Live, that the angle of elevation was actually 53 degrees. So plugging these values in, and again, this was what the other spreadsheet looked like when we had a range of values, but if we plugged in the real world data, we get a pretty good result, 0% error. So again, I'm going to have to give this point to Red. Picking any arbitrary numbers will not work with these calculations. So that's it. 6 up, 6 down.
5. Okay, now you do.
Oh. This way. Oh, shoot.
So, are there lessons to be learned from this story? Yeah, here's a little parable for you. Take a guy, we'll call him Joe. Joe's got a YouTube channel, and Joe's really interested in spelunking. You know, he just loves crawling through those caves. So he makes a video called Spelunking 101. Now, is it possible Joe made some mistakes? Yeah, he might have made some mistakes. Maybe he didn't. But now we've got another guy named Reggie. And he also has a YouTube channel. And he makes a video called Spelunking 101 Debunked. Now, is this just a case of 2 guys and 2 videos? And the answer is no. It is not that at all. Because Reggie is specifically going after Joe, specifically debunking his video, then does that mean he's questioning Joe's integrity? I mean, that is a possibility. If he's going after him like that, maybe he is. So the bar is set much higher for Reggie than for Joe. Remember, Joe might have made a mistake. You know, he might have made a mistake in his video, but Reggie is essentially calling Joe out. So if Reggie makes a mistake, I mean, he's basically calling Joe a liar, but, you know, Joe might have been telling the truth, right? The bar is set much higher for Reggie than Joe. So here's here's what Reggie must do. He must absolutely watch Joe's video carefully. He must understand it completely. And he must be 100% sure that Joe is in fact wrong. If he is to go after Joe, he really has to have his bags packed. So are there examples of not following this advice? Yeah, absolutely. We already talked about them. So again, Soundly made a video, curved water found, and one of the main premises of that video was that these power lines were in a perfectly straight line. That's why the observation works, is that the power lines are in a straight line. And then 3 weeks later, Dr. Zack, you made a video, Curved Water Found Debunked. You even used the title of Soundly's video. But in your video, you've got the wrong power lines. I mean, that's a foundational error. And that's an error that could have been avoided by simply watching Soundly's video. Now, moving to the present, Red's Rhetoric made a video on the ISS finding the altitude. And again, a central premise of his video is not that he's wonderful and he does all these wonderful things with math. A central premise is that you can do this yourself. He even shows you some cameras, some inexpensive cameras you can buy if you don't want the P900. And then you come along a month later and you make a debunking video, very, very specifically calling Reds out. But you made 6 huge errors, which I've detailed in this video. And again, some of these errors could have been avoidable by just simply watching Red's video. I mean, just simply watching it and carefully understanding what Red was saying. So again, it's always good to live your life as an example to others, not as a warning to others. So I'd like to send out some thank you. So please consider subscribing to Red's Rhetoric. Please subscribe to Astronomy Live, and please subscribe to Dr. Zack's channel. Here's my Patreon page. I figured if Dr. Zack can have a Patreon page, then so can I. So if you contribute, you will be supporting my family with my crazy kids. So thank you in advance for supporting my family. And thank you again to Dr. Zack for being able to take a joke, being able to, poke some fun at yourself. It's always good to have a sense of humor. So Dr. Zack, hopefully this wasn't too painful for you. You could let us know that there's no hard feelings. Just give us a $1 million smile, Dr. Zack. All right, that'll have to do. So why don't we end up with a quote? Treat everyone with politeness, even those who are rude to you. Not because they're nice, but because you are. Thank you.